Assalamualaikum warahmatullahi wabarakatuh. Let's continue to our lesson. So for today, we will learn about the properties of mixture part 2, where we already covered the topic in part 1. So we will already cover this topic in part 1. So for part 2, we will see the colligative properties and also the phase diagram of mixture in this topic. So I hope you already understand all of this lesson in the previous chapter, where all of this is important for you to understand better the lesson in this topic. So we will see the colligative properties. An ideal solute has no effect on the enthalpy of a solution in the sense that the enthalpy of mixing is 0. However, it does affect the entropy by introducing a degree of disorder that is not present in the pure solvent. Previously, we found that the equation that is delta S more than 0 when two components mix to give an ideal solution. So we already see this in the previous chapter where we introduce or when two components mix to give an ideal solution, the entropy will be more than 0. We can therefore expect we can therefore expect a solute. When introducing a solute, the solute will modify the physical properties of the solution. Apart from lowering the vapor pressure of the solvent, which we have already considered, a non-volatile solute has 3 main effects, which are: it raises the boiling point of a solution, and it lowers the freezing point of the solution, and it gives rise to an osmotic pressure. Of course, the pressure will be increased too, and also the density will be changed too. So we already covered this in previous chapter. So we will see these 3 factors in this chapter. So colligative properties does occur when dissolving solute in pure liquid, such as when we introduce salt in our water. Of course, what we will see, the physical properties of the solution will be increased, such as the boiling point and freezing point. The boiling point will be increased, and the freezing point will be lower. Because this property all stems from change in the disorder of the solvent, and the increase in disorder is independent of the identity of the species we use to bring it about. And all of them depend only on the number of solute particles present, not their chemical identity. For this reason, they are called colligative properties. So, colligative property, in a simple word, we can state that the properties of a liquid or a solution that change when a solute is added, where the magnitude of the change depends on the number of solute particles in the solution, not on the entity of the solute particle. So this is what is colligative properties. The property that change when another element are introduced in the solution. So this element we call it as a solute. So for example, we can see that in colligative properties, the elevation, the raising or increasing in boiling point, also lowering in freezing point. So here is the formula how we calculate the boiling point. TB is the temperature of boiling point, and TF is temperature of freezing point. So each element have their own constant. So here, for example, we can see that the formula of boiling point is TB, that is temperature at the boiling point, equal to KB and BB. What is KB and what is BB? KB is ebullioscopic constant, and BB is the molality of solute. So for the formula of freezing points, TF is temperature at freezing point, equal to KF and BB. KF is cryoscopic constant of the solvent, and also BB is the molality of a solute. So why this happen? So because when we add a foreign element, or in this case is a solute in the solvent, so we will have another process where if we have only water in our solution, we already have only water-water interaction. But when we introduce a foreign element such as sodium chloride, so now we already have a few interaction in our solvent. For example, we will have solvent interaction, solvent interaction, solute interaction. So we already have a 3 interaction in our solution. So that's why we need more energy to overcome all of this interaction. That's why there is increasing in the boiling point, and also depression of a freezing point. The logic is the solid is not volatile, therefore it does not appear in vapor. Boiling point is elevated when solid inhibits solvent from escaping in the vapor pressure, while the solid is insoluble in the solid solvent. Solid inhibits solvent from crystallizing. So because of this, we need more energy here. So we need more energy to overcome all of the interaction. That's why there is increasing in boiling point, and also decreasing in freezing point, because more energy need to overcome all of this interaction. So when we have, for example, if we only have water in our solution, we only have a solvent interaction or water interaction only. However, when we have another foreign or another element, so there is more interaction. More interaction leads to more energy, and more energy leads to rising in boiling point. So next, it's about osmosis. Osmosis is the phenomenon of osmosis is the passage of a pure solvent into a solution separated from it by a semi-permeable membrane. So osmosis is a spontaneous movement of a pure solvent across a semi-permeable membrane. So if we can see what you see, the fact it's like a pot of tea, cup, and a sieve. So what does membrane do? A sieve is like membrane, it separated or integrated. the water and also the powder. So that is how osmosis work. So in osmosis we will have a membrane. Membrane is semi-permeable in character. So membrane a membrane is permeable to the solvent, but not the solute. For example, if we have water and sodium chloride in our solution, only the water can cross the membrane, while the sodium chloride will be retained. It is because in membrane is like the seal, where it have a pore, so only molecule that is smaller than pore can pass through, while the molecule that is bigger than that will be retained. The osmotic pressure, while the osmotic pressure is the pressure that must be applied to stop osmosis. So here is a few examples of picture of the how the membrane works, where we have here is a membrane where we have like this. What here is the only molecule that less than the pore of the membrane can pass through. So the osmotic pressure of a solution is proportional to the concentration of solute. So it can be described as a Van Hoff equation. So if we can see clearly, this Van Hoff equation resembles the perfect gas equation, where our perfect gas is PV equal to nRT. So here we have pi, V, and V is a molarity. Sorry, NV is a mole, R is a Riemann equation, T and T is temperature. So when we move this one, V, to our right hand side, we will have a B, concentration of B, or a molar concentration. So here is the simplification of a Van Hoff equation. So you can use either this one or this one. So it depends. It depends on the equation. So here is the application of the osmosis. For example, cell, this is an isotonic solution. So what is the isotonic solution? The isotonic solution is the concentration. The concentration in and out of the environment is equal. So thus the net movement of water in and out of the cell is zero, because the concentration of solute inside and outside the cell is the same. While in a hypertonic solution, the concentration of solute outside the cell is greater than the inside. So there is a net flow of water out. So water will be out from the cell, causing the cell to dehydrate, shrink, and will be die later. And while for a hypertonic solution, the concentration of solute outside of the cell is less than the inside. So there is net flow of water into. The water will come into the cell, causing the cell to swell, and perhaps it will be burst when there is more water in the cell. So this osmosis properties helps molecular cells to maintain their structure.